Okay. So I'm going to put four words, or four, I guess, words and phrases up here on the board. And if anybody feels comfortable talking about any of them or explaining any of them or telling me what they mean to you, that would be fine. If not, I'll tell you what they mean to me. Anybody have a thought about any of those? You don't have to talk today, it's okay. But if you do want to talk, anybody have a thought about any of those? They're all familiar words, Maren.
Is it the vertical line test where you test to see only one point is on the same line?
Exactly, and when I do that, what am I testing to see? What am I checking for?
There's only one X value.
And what would that mean if there is only one X value for each Y? What would that mean?
That it's a function.
That it's a function, exactly. So the vertical line test is a test to determine if something is a function. So for example, in tonight's homework, which again, let me say, you do what you can do. You do it when you can do it. This week, we'll continue to have assignments. I'll continue to blather on about mathematics, but you will do it when you are ready to do it. Okay? No pressure, no stress. Do it when you're ready, as you're ready. So tonight they'll give you some pictures, and you will, and the question is it a function or not? So Maren has said one way to tell that is to pass a bunch of vertical lines down through the curve. You can do that mentally, you don't have to actually draw the vertical lines. And every vertical line you draw is allowed to hit the curve in no more than one place. I'm drawing vertical lines, and I'm allowed to hit the curve in no more than one place. So that one would be fine, as opposed to a picture like this, though, where you draw vertical lines down through and they hit the curve in more than one place. Remember that? And that test actually is because of the definition of a function. Does anybody know what the definition is? It's a set of points. And what about those points? By the way, a set of points is also called a relation, so that's another word you should probably be comfortable with at some point. But what about that set of points? It's not just a set of points, it's something else. A set of points that what happens? No, like Maren said, no first coordinates. A set of points in which no first coordinates, which I think you said, Maren, x's. Those are the x's right in order pair, that'd be x comma y. Now, I do want to say I'm not going to use x's in my definition because eventually we're going to go to a different coordinate system. So instead of having x's and y's, we'll have a different kind of ordered pairs. And a function is which, in every ordered pair system there is, no first coordinates repeat. You can't use them more than once. So the graphical test for that is you pass lines down through vertical lines, and none of them hit more than once. Okay, very good. Okay, so the vertical line test is a test for function, to see if something is a function, and to accomplish it, you just see if any vertical lines hit the curve more than once. Very good. How about these two words? Anybody, I know you've seen those words before. Does anybody have a thought about those two words? Okay. Oh, go ahead, Mr. Fisher, sorry.
A domain is the x and the range is the y.
Exactly. If we look at a set of ordered pairs, I mean, think about it, kids. Look at a set of ordered pairs. I'll just make up a set here. That would be a function, right? Because none of the first coordinates are repeated. And if we looked at just the first coordinates, that set the set of first coordinates, that's the domain. And then the set of second coordinates, that's your range.
So it's x and y?
Yeah. Now, be careful again, Isaac. It's okay right now to think about it as x and y, The problem's gonna be when we go to our circular graphing system, we're gonna be graphing things on circular graph paper like this. And those ordered pairs aren't X and Y, those ordered pairs are R comma theta, but they operate the same way. So I'd rather not necessarily think about it as X comma Y, but maybe first coordinates and second coordinates. But it is, for now, it is X comma Y, absolutely. Okay. Now there are tons of stuff. This is one of those huge sections in the book. It's one section, 1-2, but it's got a billion ideas in it almost. I mean, there's a lot of ideas. So I'm going to hit a couple of them today. We'll hit some more tomorrow. This idea of domain is probably one of the most important ideas we're going to talk about in this entire chapter. So let's start this conversation by me putting a couple of functions up here. I'm just making these up. These are random functions. You've seen these kind of functions before. I'm going to put a couple of new ones up here. We've really not talked much about that or this. And the question is, for all of these, and these are just random functions, I think I'll put a couple more up here. The question is, what is the domain of these functions? What is the domain? That's the question. Now, if you were listening to Isaac a moment ago, Isaac said, is that just the x's? And my answer was, yeah, pretty much. That's just the x's. So, what can you tell me about the x's for that very first equation up here? This very first one I started with right here. What can you tell me about this equation? What would this look like if I drew a picture of it? That would be a line, right? That's mx plus b, so that would be a line. So what can you tell me about the x values? If you were going to draw this line, what x values would you be allowed to use? Because that's what we're talking about, domain. That's x values. What can you tell me about those x values? What do you think? What? You can choose any. So how will I say that as a mathematician? I mean, it's okay, yeah. I can just, all real numbers. Very, very good, Janet. All real numbers. The domain for this one is the set of real numbers, and that's the symbol for real numbers. So you can either use that symbol or you can write out the word real numbers. Now, I want to get something straight here, and I know we're kind of, some of us are listening, some of us aren't, and that's okay. I'm going to say this about 12,000 times this year. In function land, the domain is always all real numbers, unless you have unless there are one of two things happening. The domain will always be all real numbers, as long as you remember the denominator can never be 0, and you can never have a negative under a radical. So I'm going to say, keep it real. Now, in math, what's the opposite of real? Imaginary. And how do you get imaginary? You take the square root of negatives. So I'm telling you that we got to keep it real, which means we can't take the square root of negative numbers, which means whatever is under the radical is going to have to be positive, okay? So as long as we don't have a denominator that's 0, and as long as we're real, our domain is going to be all real numbers. So I want you to look at this one. Does this one have a denominator? No. So we don't have to worry about the denominator being 0 because there isn't a denominator. Is there any chance of this not being real? No, because what's the only way you can be not real? The square root of a negative. And if you don't have a radical, then you're not going to be imaginary. Would everybody buy that? So when I look at this problem, there's no denominator to be 0, there's no radical to be negative, so guess what the domain is for that problem? All real numbers. Remember, it's always all real numbers unless you've got one of these things going on. This is what changes the domain. Okay, so I'll look at this one. Now wait a minute here. This one has a denominator, right? The denominator can never be 0. So what does that tell me about this x value, possible x values here?
Has to be greater than
Doesn't have to be necessarily greater than 2, it just can't be equal to negative 2. Do you see what I mean? I'm looking at this problem right here. The denominator can't be 0. So that means x can't be negative 2. Would you agree with that? Remember, the two things that cause you issues with domain are denominators and radicals. You have a denominator. You got to be careful. The denominator can never be 0, so x can't be negative 2. Now this is perfect for me. I am perfectly happy with that answer. When you look in the back of the book though, it's going to say this. Do you understand that that is the same as this? What does this say? Go everything less than negative 2 and everything greater than negative 2? Isn't that everything except negative 2? I'm okay with this. I'm just telling you when you look it up, it's going to look like that in the back. All right, now let's look at this one. Hey, wait a minute. Do I have to worry about the denominator being 0? For this problem? No, no denominator. I don't need to worry about that. But I have to make sure it's real, which means that whatever is under here, x plus 4, it has to be bigger than or equal to 0.
So nothing less than negative 5.
So I have to look at numbers bigger than or equal to negative 4. Just solve this little inequality. You know that what's under the radical has to be positive, correct? So x plus 4 has to be bigger than 0, which means x has to be bigger than negative 4. That's my domain. For this problem, that's my domain. I'm just fixing my attendance here. All right, let's look at this next one. Okay, let's take a look at this one. Remember, if you have to put your head down, that's fine. All right, let's look at this. What do you think? What do I have to worry about? Remember, these are the two things that cause me issues. I don't see a radical there, do you? So I'm not worried about imaginary numbers. I'm good, no radicals. But what do I have? A denominator. And what do I know about my denominators? They can never be 0. So 3x plus 5 cannot be 0. Now some of you can look at this and tell me, okay, the domain is x isn't equal to negative 5/3. Some of you may need to actually solve that out. It doesn't matter. Denominator can never be 0, ever. So that says that x cannot be negative 5/3. All right, now let's look is a different situation. This is a radical. So what do I have to focus on? Keeping it real, which means what? No imaginaries, which means this guy has to be bigger than or equal to 0. Because if I want to be real, don't I have to have a positive number under here? So what's my domain? X is what? Greater than or equal to negative 5/3? Uh-oh. Double trouble. Right? Why do I say that? I got both issues going on, right? So the first thing, the easy one for me, is I look at that denominator and say, okay, whatever x is, it cannot be 3. Would you agree with that? You can't have a denominator equal to 0. The denominator can't equal 0, so x can't be 3. What else can you tell me about x? Well, whatever is under the radical has to be positive, which means x has to be bigger than or equal to negative 2. And I am okay with you writing it that way. Do you understand what that means? That means x is every number, or could be, x could be every number bigger than or equal to negative 2, except 3. You have to skip 3, because that would make the denominator 0. You okay with that? Okay. The next thing, the next big idea that we need to talk about is continuity. That's a big math word, an important math word. By the way, I'm taping this so that those of you who may want to come back and watch it another time, you'll be able to get the notes. Discontinuities. There are really 3 kinds of discontinuities. There are removable, non-removable, and jump. Now that word discontinuity means nothing to you because we haven't talked about continuity, what it means to be continuous. There's actually a big long definition of continuity. I observed the calculus class yesterday, and they were actually proving things were continuous yesterday. It's kind of fun. For us, at this point of our career, if you can draw the picture without lifting your pencil, it's continuous. So that would be an example of a continuous function. I draw it in one big swoop, it's continuous. How about a parabola? It's continuous. How about one of these guys, though? Do you remember these from last year? Those are called step functions or greatest integer functions. Janet, you've never seen those before, or was that a yes? You have seen those before, yeah. They're called step functions or that's a picture of the greatest integer function. This is a perfect example of a jump discontinuity. Does that kind of make sense to you? It's discontinuous because you draw it in pieces. Do you understand what the word jump means? The pieces are jumping up, as opposed to a picture like this, which you also drew last year, hopefully. These are called hyperbolas. Now they're discontinuous because I've had to draw this piece, then I got to pick up my pencil and draw this piece, but that's not a jump. It's an issue, but it's not a jump discontinuity. All right, so what do we mean? I think these are kind of easy. I mean, you can kind of tell when you've got a jump discontinuity. They look like that. These, what do I mean by these words? Well, The easiest thing to do is for me to give you a couple of examples. Okay, so here are a couple of examples. We're going to use our calculators to help us graph these, but first we're going to talk about the discontinuities first, and then we'll finish the graph with our calculator. Soon we'll be able to do these in their entirety, but today's not the day to tackle that. So we're going to use our calculators to help us. But let's talk about the discontinuities. What's the domain here? Anybody know? For this first one here, no, just that first one? What would the domain be? X can't be 3, right? Cannot be's, when he says to me, X cannot be 3, a cannot be is graphed as a vertical asymptote. So when Jared says, X cannot be 3, and I hope everybody sees that because that would make the denominator 0. When he says it can't be 3, that tells me that where X is 3, I'm going to have a vertical asymptote in my picture. That is a non-removable discontinuity. A vertical asymptote is a barrier that you cannot cross because X cannot be it. No negotiation. It cannot be. When you graph this function on your calculator, and those of you that have a calculator, I'm going to ask you to do that if you want, if you can right now. If you type that in, you will see that asymptote. Now, when you type it in, make sure you put your numerator and denominator both in parentheses. It won't work if you don't. I mean, you'll graph something, but it'll be the wrong thing. I just have a standard window. I don't know how yours is set from yesterday yet, but this is the picture I see on my calculator. Now, my calculator doesn't show a dashed line. Does yours? Does it show an actual dashed line? No. Here's what the calculator does. Remember, this is discontinuous. What does discontinuous mean? When I draw it, I have to lift my pencil. Your calculator can't do that. So it drew this piece, and then what did it do? Shot up and drew this piece. That's an asymptote. That's not part of the graph. That's simply your calculator trying to get from this point to this point. It just goes straight up and then draws that second piece. But that asymptote is there. Well, we'll talk more about these tomorrow, all right? Did anybody not make it? Malcolm didn't, and Heidi didn't, and Audrey didn't. Did everybody else make it? All right, listen, you guys take care of each other, all right? That's what you do now. You take care of each other. You take care of yourself, take care of each other. Anybody want to do Math League sign up today? We can do that now.